So far we've been using sort of an intuitive notion of what a linear system of equations is, but it pays to be really precise about what exactly we're talking about. So a system of linear equations is a collection of equations that looks like this. So all of the a's that you see here, these are in a particular example of a linear system, all of the a's are just going to be actual numbers, all the b's as well. And the variables are the x's. So there are a lot of subscripts here. So let me sort of explain my subscripting notation, which is pretty standard. The first subscript, so on the a's, the first subscript is the row number that you're on, or otherwise known as the equation number that you're on, right? So the first equation, this first subscript is 1, the second equation, the first subscript is 2, and so on, all the way down to m. M is the largest row number, so it's actually the number of equations. So m is the number of equations. Notice that on the right-hand side of the equation, these b's, these are also all constants, and since there's only one b value for each equation, the subscript on the b's is actually the same as the first subscript on the a's. Right? So the b's go from b sub 1 down to b sub m. On the a's, the second subscript is which variable you're on. So notice that the variables also are subscripted, since, unless you're talking about a particular system of equations, you don't know how many variables you might have, and so you need to sort of number them, because you can't use different letters because you don't know how many letters to use. So the variables, the x's, also have subscripts, and they go from 1 to n in every equation. Right? So in a general linear system, every variable could show up in every equation. So every x from x sub 1 up to x sub n shows up in every equation. So n is the largest subscript on your x's, so n is actually the number of variables. So we will call this kind of system an m by n system. So n equations and n variables. And also m rows and n columns on the left-hand side. So that's how the subscripts work. And a linear system is just you have numbers times first powers of the variable. So a number times x1 plus a number times x2 plus and so on, all the way up to a number times x sub n equals some number. And that's the first equation. And then same thing for the second equation. It's some other number times x1 plus some other number times x sub 2 and so on up to x sub n equals some different number on the right-hand side. And so on all the way down to your last equation. So this is a linear system of equations. I should mention that really a linear system of equations is any system of equations that you can rearrange to look like this. So, even if one of the x's started out on the right-hand side, that's fine because you can move it to the left-hand side. But this is sort of the standard way to write a linear system of equations, with all the variables on one side and the constant terms on the right-hand side. And then just to keep our bookkeeping nice, it's a good idea to have the variables sort of aligned vertically. It just sort of helps the eye understand how everything is set up. Okay, so the x's are our variables. All the a's, those are our coefficients, and the b's are the constants on the right-hand side. Sometimes the a's and b's, they get called, they're numbers, but sometimes numbers get called scalars for reasons that we'll talk about later in the quarter. So a solution to a system is basically what you think it is. It's a value for all of the variables, and I've called the values for the variables. I've put primes on them just to distinguish the values for the x's from the variables that are the x's. So a solution is just a collection of values for all of the variables so that when you put the values into the variables, it makes all the equations true. So that's our usual notion of a solution to an equation. So hopefully this definition is no surprise. A system of equations is called consistent if it has a solution. It could have more than one solution. But if it has no solutions, then the system is called inconsistent. So an inconsistent system is one that's really a contradiction, or a system that's asking too much and making things impossible. So that's why it's called inconsistent, because it kind of contradicts itself, so there are no solutions. Finally, the last definition I want to make is just that if all of the b's on the right-hand side are actually zeros, then the system is called homogeneous. We'll see later that homogeneous equations are sort of the nicest equations, and we'll have the most tools to deal with homogeneous equations. Just to give you an idea of what makes a homogeneous equation special, let's look at a 2x2 case. So maybe x plus y equals 0 and x minus y equals 0. So if we graph this system, x plus y equals 0 turns out to be this line, and x minus y equals 0 is this line. And the fact that the right-hand side of both of these equations is 0, that's what makes both of these lines go through the origin. So the reason that homogeneous systems of equations are the nicest is because all of the lines, or planes, or hyperplanes, all go through the origin of the coordinate system. And it turns out that will have some geometric consequences that make homogeneous systems the nicest kind of system. But in general, most of our systems won't be homogeneous, in which case the right-hand side are all b's.